We're going to continue to solve oblique triangles, which are non-right triangles, utilizing now a new property we're going to call the law of cosines. We're going to go through and derive that for you in a few minutes. Before I do so, I just want to review the other types of problems that we've worked with so far with the law of sines. Okay. First of all, we've talked about the law of sines. And we know that little a over the sine of a equals little b over the sine of b, which equals little c over the sine of angle c. Okay, so that's our law of sines, and we've proven that before now. We've used that to solve different scenarios, different triangles, where you're given different information about the triangles. So, for instance, we've seen that if you're given two angles, you could be, two angles and then any other side. So, two angles and the side between them, or two angles and a side not between them. Doesn't matter which one. So, we call that the angle side, or the angle side angle. But in either scenario, you have two angles and a side. This is the easiest scenario to solve because once you know two angles, you can immediately get the third. And so once you have all three angles plus one of the sides, you can fill in one of these three ratios and solve for the missing information in the other ones. Okay, so it's very simple once you know two of the angles. So that was the first type. Those were the first types of problems that we saw. Then we looked at the ambiguous case. Remember, the ambiguous case occurred when you had an angle, a side, and a side, but not the other two angles. Okay, so the ambiguous case was an angle. Well, you know what? Let's not call it the angle side-side. We'll call it the side-side angle. There's a reason we don't call it angle side-side, if you know what I mean. It doesn't look that nice. So we'll call it the side-side angle. And that's where you could have 0 triangles or 1 triangle or 2 triangles, depending upon how the sides match up, the lengths of the sides. Sometimes, if you have an angle, a side, and then a side, if one of the sides isn't long enough to reach down to the other side, then there's no triangles. If it's really long, you only have 1 triangle, and if it's kind of in that middle ground, you could have 2 triangles potentially, depending upon how that plays out. So that's the ambiguous case. That's where you have multiple options. But there are other types of triangles, other types of given information that we can have that would solve a triangle as well. For instance, if I knew all 3 sides but no angles, I can actually solve for all the angles. If I have all 3 angles but no sides, that doesn't work. You can't actually solve those triangles because with all 3 angles given, the sides could be a variety of things. You just get similar triangles, not congruency. So we could say that angle doesn't work. So really the only other option, here we've got 2 angles and a side, here we've got 2 sides and an angle. The only other option that we have left is where you have 2 sides and an angle, but the angle comes between the 2 sides. Okay, so instead of side angle, it's more of a side angle side scenario. Okay, and that's where we're going to utilize the law of cosines, is with a side angle side situation. You have 2 sides and an angle, but the angle is the angle that's included between the 2 sides. Okay. All right. So now here's how we're going to derive the formula. It's called the law of cosines. We'll derive this for a moment. The first thing I'm going to do is I'm going to take this triangle ABC, and I'm going to put it on a coordinate axis, a set of coordinates. In fact, I'm going to run my x-axis and my y-axis through vertex B So vertex B is at the origin, and my x-axis runs along the line BC, or the side BC. Okay. Now, it's kind of interesting. So point A has coordinates, right? In fact, all these points now have coordinates. So point B has coordinates 0, 0, because that's at the origin. Point C, over here, well, notice this side BC has length A. So side C is A units over to the right, so it's A comma 0 for its coordinates. Okay. Now point A up here, we don't know exactly how far over and how far up that is. So I'm just going to call it X and Y. It's got XY coordinates, right? So I'm going to call that A having XY coordinates. Now what we are going to be able to do is make some expressions for X and Y in terms of A, B, and C. All right? So let me show you how that's going to be done. First thing I'm going to do is I'm going to draw in a perpendicular line segment from vertex A down to side A. Right? That perpendicular is going to be given a name. We're going to call it Y. Yeah, that's the height of that point, right? So Y is there, X would be this other side coming over, but we don't need that. So we're just looking at the vertical value there. That's Y. It's the Y coordinate of that point, right? Same thing as this Y. So now if I look at angle B right here, because that's my central angle, I know that the sine of B is opposite over hypotenuse, so it's Y over C. I also know that the cosine of B is adjacent over hypotenuse. Oh, I do need the x. What was I thinking? So this distance here is the x value of that point for A, right? So that's going to be the adjacent side. Adjacent over hypotenuse is x over c. C being the hypotenuse for that right triangle. All right. Now, if I were to solve for x and y respectively, I multiply both sides by the c. So multiply both sides here by c, multiply both sides here by c, and what you'll get is y equals c times the sine of big B, and here x equals c times the cosine of big B. And it's a little c. It's supposed to be little c. There we go. So little c sine B, little c cos B. All right. So now I'm going to take those two expressions and put them in for my coordinates, so that vertex A not just is xy, but now it's c cos B, c times the cosine of big B, comma, y is c times the sine of big B. Okay? So now let's consider side little b. That's the one we really haven't considered yet. We've looked at A and C. Little b over on the side can be found, that length can be found using the distance formula between 2 points. Right? The distance between 2 points, we'll call that side B, is found using the distance formula. We've seen the distance formula before. It comes from the Pythagorean Theorem. The distance formula is the difference in the coordinates in the x direction and the difference in the coordinates in the y direction. That makes up the two sides of the triangle there, and then you square those differences and put them under the root. So you'd have, in the x direction, you'd have the distance between C and A, which is A minus my cosine. Actually, I'll do it the other way around. We'll do the A point minus the C point. So we have C times the cosine of B minus little a squared plus c sine b minus 0. C times the sine of b minus 0 all squared. Okay? So that's our distance formula. Now, from this distance formula, I can simplify stuff under the root. So I get b is equal to, actually, maybe before I even do that, let's square both sides. It's an equation with a root. If I square both sides, it eliminates the root, right? So let's call that b squared, and then let's just forget about the root. So the stuff underneath is c times cosine b minus a squared plus, now if I'm subtracting 0, I really don't need the 0 in there, so I'm just going to call this c squared sine squared b, right? I'm applying the square to both those factors. The 0 is gone, so I don't need it. Cool, so I've got a bunch of things squared. Now I'm going to square this, I was going to call it a binomial. It's got two terms. It's not really a polynomial, though. I'm going to square this expression, okay? C cos b minus a times itself. Let me take that off to the side for a moment. I'm running out of room. Now let's take it over here. So I want c times cosine b minus a times itself. Okay. And then when I distribute, it's going to be c squared times the cosine squared of b. Then I'm going to get c cos b times negative a. Then I'm going to get another negative a times c cos b, so minus a c cos b. Negative a makes it plus a squared. Squeezed it in. Alright. Hopefully you can see that okay. It's pretty small. Anyway, I'm just expanding it out. I'll put the final form here. It might be a little bit easier to see. So that's going to be, I'm just going to copy this. Oh, I'm going to combine these two terms in the middle. It's going to be 2ac cos b. So I get, what's that? C squared cosine squared b minus 2ac cosine of b plus an a squared, and then I have this plus c squared sine squared b. There it is. So I've expanded the right side of that equation. Now I could do some grouping. The c squared cos squared b and the c squared sine squared b. If you notice, they both have a c squared. So what I'm going to do is get those two terms together. I'm going to call it c squared cos squared b plus c squared sine squared b. I have this plus a squared and a minus 2ac cosine b. Right? So now I have a common factor of c squared from two of the terms. I'm going to pull that out. That should be b squared. That's my square there. C squared. Now I have cosine squared b plus sine squared b. Alright, now I'm going to have to start erasing because I've filled everything in. But basically we have b squared equals c squared times the quantity of cos squared plus sine squared plus a squared minus 2ac cos b. That's long. But here's the cool part. By factoring out the c squared from these two terms, cosine squared of something plus the sine squared of the same thing is equal to 1. That's a Pythagorean identity. So that expression is really just equal to 1. So, let me get rid of a little bit of this stuff. And what I really have then is b squared equals c squared times 1, so I don't need that anymore, that stuff's all gone if you multiply by 1, plus an a squared minus 2ac times the cosine of b. Right? Now, we tend to write this in a slightly different order. I would tend to write this alphabetical and put the a squared before the c squared. It doesn't really matter, but it's just kind of a general formula. So we'd have b squared equals a squared plus c squared minus 2ac times the cosine of b. This is going to be our law of cosines, one of them. What's interesting about this formula is that you have three terms here that are basically the square of the three sides. Right? You've got a b squared, an a squared, and a c squared. And then you have this extra thing that you're subtracting off. It's 2 times ac times the cosine of b. The reason this is called the law of cosines is because it has a cosine in it but no sine. Now, if you look at the pattern here, notice that on the right-hand side you have angle B, right here at the origin, and you have sides A and C, which are the two sides adjacent to angle B on the triangle. Okay? So you have A and C and the included angle B. A and C, the included angle B. On the other side of the equation is just the opposite side from that angle, B squared. Okay? So, things are separated out kind of nicely. You have a side and its opposite angle, and in between here you have the adjacent sides. Okay? Now, I drew this triangle with B at the origin, but I could have reoriented that with any of the vertices at the origin. I could have put A there, I could have put C there. It would have recreated the formula with some of the variables in different places. And so I'll show you what would have happened. I'm not going to go through all this. It's exactly the same algebraic steps of expanding and simplifying and canceling some stuff out. It's exactly the same steps, just with the letters in different places. And so what you would get if you move and put the vertex A or the vertex C in that spot is a different formula, where you have a squared equals b squared plus c squared minus 2bc times the cosine of a. Notice when I wrote that out, I have a side on one side and an opposite angle. So little a, big A are on the outside here. And then in the middle you have the B and the C, the other two sides, the adjacent sides to A. Right? A, you got B and C, so A is included between the B and the C. The other form, with C at the origin, would be C squared equals A squared plus B squared minus 2ab times the cosine of C. Right? So again, you've got a side and its opposite angle on either side of the equation, and then in the middle here you have the adjacent sides to that angle, A and B. Right? So you've got little c, big C on opposite sides of the equation, and then the adjacent sides to C, which are A and B, are going to be the two sides on that side. Okay, now, so there are three different forms of the law of cosines. Erase some of this other stuff now. Okay, so here we have three different forms of the law of cosines. All three of them are valid. I think if you memorized one of them, the other two would be pretty easy to come up with. You just switch around the letters, right? What's very interesting is that if you recall, if I were to take this triangle and make it a right triangle, we've done right triangles quite a bit, so recall a right triangle for a moment. Let's try it the other way. let's make a right triangle, and let's put C as the 90-degree angle. On a right triangle, if you were to put C as the right angle, the cosine of 90 degrees is 0. Cosine of 90 degrees is 0. And so you end up with this thing, when C equals 90, that whole thing equals 0. Oops. I'll say that equals 0 when C equals 90 degrees. Well, if that equals 0, then this whole term wipes off. And so when C equals 90 degrees, your formula becomes, let's keep it in red, C squared equals A squared plus B squared. I hope that's familiar to you, because that is the Pythagorean theorem, the original Pythagorean theorem. And so the Pythagorean theorem really is the law of cosines, where one of the angles is 90 degrees. Works out very nicely. So it's kind of a neat way to remember this. I kind of remember this one. This is the one that I choose to memorize if I'm going to memorize one right here, because it starts out with the Pythagorean theorem, C squared equals A squared plus B squared, and then you just subtract off 2AB times the cosine of C. Okay, and so I can remember that one, and then just make all the adjustments from there. So just a thought, you know. So anyway, what we're going to do in the next few videos is just give you some examples of how to solve some side angle side situations using the law of cosines now. Okay, but the main thing is, if you know two sides in an angle, the included angle between them, then essentially you can use any of these formulas, fill in everything on one side of the formula, and that'll allow you to solve for the other side. Okay, and that'll give you the third side of the triangle. And then from there you could use the law of sines, or a variety of other things to find the other missing pieces of information.